But yeah, I'll see you all, next week for that. Also, the lab today, that's what I want to talk about next, is not due next week. It's actually due by the end of finals week. But basically, I didn't want to, since the stuff from the math from lab today, we're really not going to finish up in class. We're going to work on it more in class tomorrow. But I'm not trying to rush you through the math because it is a little bit more, well, I mean, once you get it, it's pretty easy, but that it takes some time to really understand some of the components. But anyways, it is due at the end of finals week. Obviously, you don't need you can finish it before the lab final if you want. You should be good to do that. But I'm just trying to give you guys plenty of time for today's lab. And if there's no questions, I'll just pause for a second. If there's no questions about the lab final, we can just move on into the last lab. So I guess we're good to go. So yeah, lab 11 is the last lab. It is on, well, essentially applications of what we call Taylor and Maclaurin series. And that's today what I want to talk about is what is a Taylor and Maclaurin series. And essentially the lab is on what it's useful for. So we're going to be, in the next couple classes, we're going to be talking about what are called established Maclaurin series. So if you don't know, if you've never seen these before, I just wanted to show you some of these formulas. But the first one you'll recognize from the power series lecture from before, or basically from the geometric series formula. But essentially a Maclaurin or a Taylor series is a representation for a mathematical function. So say, for example, the natural exponential function e to the x, you can actually express it as an infinite series of polynomials. Similarly with sine and cosine, they have what are called power series representations. So the first question is, well, why and how do we figure these things out? Because if, I think the more advanced level of mathematical understanding that you have, the more these formulas look really weird. It looks very strange, like why these things can seem like they make no sense. And so, today that's what I want to talk about is how was this idea uncovered? And then, we'll continue to work with them for basically the rest of the semester. The week and a half of class, we're going to just talk more about these, starting with the basics and then moving into why are these so relevant. And, I think to me, this is one type of math that's really fun. I think it's pretty exciting. And also it's sort of like in my mind, it's kind of the whole point of why we've been talking about series for the last 3 or 4 or however many weeks, where we've been talking about all of these tests. So we spent, weeks talking about the integral test, the comparison test, the root test, the ratio test, blah, 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 ways to figure out if an infinite series converges or diverges, right? And we've been so far looking at very specific cases and how to use certain tests. But in my mind, the whole point was to kind of get to the ratio test because the ratio test is actually the easiest way to examine power series, as I got into in the lecture videos for figuring out basically what we call the interval of convergence. Where does this series converge for? And again, it's very important to know that because if you're using these formulas, these what we call Maclaurin series formulas, these formulas don't necessarily work for every particular value of x. Like if in the example with the geometric series example from the previous from the lecture video, these only converge they have an interval of convergence from -1 to 1. Basically, it has to be a fraction, a fractional value to be able to use this formula. It is not valid, say for example, for 3. If I just plug in 3 into this, that will obviously not make sense, right? Because if I plug in 3 into an infinite series, that's going to diverge astronomically, right? 1 plus 3 plus 9 plus 27, 3, there's no way that makes any sense. That can't be equal to -1/2, right? So obviously it's like these formulas can seem like nonsense, but they're nonsense only if you're looking outside of the interval of convergence. You need to know when they converge for. It actually turns out that the convergence of the three other very interesting examples that we're going to work on today and tomorrow actually have an interval of convergence of all real numbers. You can actually plug in any real number into these formulas and they actually work, but we'll get to that soon. But basically the ratio test is how we can figure out if a power series converges or not. And again, that's obviously important. So in terms of actually using these things, so I wanted to also talk about the lab before we get into Maclaurin series, and another reason why those formulas are so useful. But basically, the normal distribution is if you've ever had a statistics course before, which I imagine some of you have and some of you have not, it's what we often call a bell curve or a Gaussian distribution. But basically, it's a distribution which represents how a lot of the spread of a lot of real data. Not all types of data, but certain types are regarded as normal. And if it's normal, it fits this sort of basic pattern where basically the average value is the highest occurrence. Like, and this is very common in, like, for example, population data, like the average height of a U.S. male or female, that follows generally a normal distribution where the average height is the most common result. And then values which are more extreme or less extreme, like higher or significantly higher and lower, are a lot less frequent. And the y-axis of basically a probability density function, as we talked about before, is where the area under the curve represents the probability of event occurring. And that's what I'm going to have you calculate in today's lab. So if you look at the question, it says the lengths of a certain population of Atlantic croakerfish are normally distributed with an average length of 10 inches and a standard deviation of 2 inches. And if you've never had stats, you might not know what that means. And that, again, that's not a big deal because I give you actually what the formula is for the normal distribution above. But basically, there are two parameters, and the mu is referred to as the average value, and the standard deviation describes basically how wide is the bell curve or what's its spread. And so in each of the following parts, your goal is to determine how many terms are needed to ensure a result is accurate to at least 1%. So basically, I give you the fundamental parameters of a normal distribution, and then I ask you to solve a couple questions. So these are the questions to be solved. And it says, number one, it says find the probability that a randomly selected croaker fish from this population will be between 11 inches and 13 inches long. But essentially, what this is saying is that, like, the average length of this type of fish is about 10 inches. So if you pick one at random, it's most likely to be 10 inches, but it could, there's a decent chance it's going to be 11 inches or 12 inches. And the probability that will be significantly larger than 10 inches will follow a normal distribution with this particular standard deviation. And so if you've had stats, there's ways of doing this without needing to do any calculus. But the actual way people figured out the math behind a normal distribution, it takes calculus, and it actually takes Taylor-Maclaurin series to do. And I don't think a lot of people know this because they just use what's called a z-table in order to figure out the probabilities. But anyways, I think it's kind of interesting because I teach stats now and again. And we do it without calculus, but essentially it's using the math that we're learning in class right now. But anyways, the idea is if we want to know the probability that we're going to select a croaker fish between 11 and 13 inches, we need to add up the area under the curve. So again, the point of a probability density function by definition is a probability density function says that the probability of event occurring, basically the probability that a croaker fish of length x will be selected between 11 and 13 inches will be equal to the area under the curve. Basically, the area under the curve will tell you the probability. And so basically that's what we would need to figure out. If we want to solve question one, I need to find the area under the curve, aka the integral of this function. So here's the problem. Sorry, this has been kind of a long explanation. The issue is the formula for the normal distribution. It's a little bit gross, but most of these are constants. But if you look at it, it says it's e to the minus x squared. Essentially, it results in an integral e to the minus x squared, which in order to solve the area, we have to solve this integral and plug in the parameters. Now, the issue is this is an example of an unsolvable integral. So if you remember, we talked about months ago, back when we were in chapter 7, at the very end of the chapter, I said that the problem with integration is sometimes they can't be solved. There is what's called no elementary antiderivative, Like, for example, e to the minus x squared. You can try to use u substitution. It won't work. You can try to do various other techniques to solve this integral. Those will not work. Basically, you cannot, the answer is not like e to the minus x cubed or something. You can't, there is no algebraic answer to this integral. So how do we do it? That's kind of where I left it off back in chapter 7. Essentially, we're stuck on certain integrals that are unsolvable. Well, you can solve them, but you need to use a series representation. Basically, the integral has an answer. It's just not a closed form solution. It's an infinite series solution. And that's the idea that we need to talk about. So kind of as I was saying a minute ago, like basically with E has an infinite representation. And another thing that you might notice about these formulas is, well, the left-hand side, e to the x, is a fairly complicated exponential function, right? Because really E is a number. It's a number about 2.718. It's a very special number. But if we take that really special irrational number to the x power, that's kind of a complicated thing, because, you know, if x is a fraction, then it means a square root of an irrational number. It's kind of a complicated calculation. What this formula says is that the natural exponential function is actually equal to an infinite polynomial. And basically, another nice thing about integrating e is very easy, right? The integral of e to the x is e to the x. But if we change it up, right, as I was just saying, with a function such as e to the minus x squared, sometimes you make a minor adjustment to what our parameters are for x, and it's impossible. There is no solution to just a slight change in e. If you just do e to the x squared, it has no elementary antiderivative. And same with sine of x squared, same deal. But however, if you look at the other side, it's an infinitely more complex, no pun intended. It's infinitely more complex because it's a infinitely long polynomial. However, if you think about taking the derivative or the integral, polynomials are very easy to differentiate and integrate. And that is why these can be very useful for applied use, you know, and that's what we're going to get into, and why in calculus 2, we focus on these things. But we'll look at a lot of other cool applications as well in the next couple weeks as we continue. But I feel like I'm getting ahead of myself because what I wanted to talk about is, you know, what is a Taylor series and how do we figure it out? And sorry, I know today's lab is going to be a little longer in terms of me talking. So let's get back into the lecture notes, and let's do the derivation of what is a Taylor-Maclaurin series. So a quick recap. So the idea that I left off with in the lecture videos was, you know, how can we use a power series? So, you know, we looked at some examples of power series. Essentially, it's an infinite polynomial, and it can have any series of coefficients. It can even be centered at another value. And the only difference is a power series centered at 0 will just look like x squared, x cubed, blah, blah, blah. And it could have whatever the coefficients are, which will adjust the convergence and so forth of the power series. If it's centered at another value, for example, at 5 or -1, it will still look very similar. Instead of being x and x squared and x cubed, it will be x minus 5, x minus 5 squared, x minus 5 cubed, and so on. But otherwise, it will be pretty much the same idea. And, you know, again, power series, to figure out if they converge, you want to use the ratio test, as you know, all the lecture videos were focused on all the details of figuring out that stuff, which is not monumentally important for understanding the basics. So with 11.9, we looked at an example of how there is, for this particular power series, 1 plus x, one of the simplest ones there is, 1 plus x squared plus x cubed, could actually be represented using a rational function. And what I wanted to show you guys before we moved on is a visualization, or how does this make sense? Because again, this formula can seem very strange, but I wanted to sort of show you it in action. And for a lot of the ones we look at, if you go into our Canvas module, you'll see I've actually just recently posted the visualization. So these we'll do these in class, but I have a link to them in class if you want to look at them and play around with them yourself. But basically, if you click on this link, it's a visualization of, well, technically you could call it the Maclaurin series representation, but again, we'll talk about what that means. I'm trying to get to that, but I wanted to show you kind of the idea and why this makes sense. But if you look at it, basically what I've designed, it's also using Geogebra, which is a tool for a geometric visualization calculator that I've used from time to time in class. But basically, I've shown you the graph of these functions. So notice that in green, it's the function 1 over 1 minus x. So it looks like a pretty typical rational function. It's got that general shape, but it's shifted. It doesn't look exactly like a normal reciprocal function, but it has a vertical asymptote at x is equal to 1 because it's undefined at 1, and it trends towards infinity as x approaches the vertical asymptote. So in blue is actually the Maclaurin series representation. And what I wanted to show you is what happens as those terms expand. And so to sort of keep track of what I'm working on is in this, basically as we work term by term by term in the expansion, 1 over 1 minus x, which is that rational functioning in green, will converge to this representation. So basically what I'm going to do is I'm going to show you, well, let's start with 1, and then we'll add x, then x squared, and look at what happens as we build that series from scratch. So if you look at the series in blue, which is G, I don't know if you guys can see this very well, but there, basically it's labeled with F and G. G currently is just a horizontal line at 1, because if you're looking at the expansion for how I define G, notice it's the sum of x to the n, which is just the power series representation as n goes from 0 to tn. So basically this slider right here, what it will do is it will add more terms. So let's say I wanted to do 1 or 2 or 3 terms. It will build basically that Maclaurin series as I continue. But notice that, so what it's just showing right now is x to the 0 power, which is equal to 1, right? So currently we just have 1. That's all that's being graphed. And right now, blue and green don't look anything alike. But the point is, as we add more terms, it should become closer and closer to the power series representation, and it will converge to the value. And I wanted to help you see the visualization of how that happens, because graphically it's very interesting. And again, these formulas, the problem with these formulas is they're very abstract. They can be hard to sort of wrap your head around. And so literally it looks kind of like wrapping a series of lines around the graph of a function. It's pretty interesting. But basically, notice now what we have graphed is the first 2 terms. It's now 1 plus x. So if you look at this expansion, right? Sorry, I've got too many tabs open. If we go to 2 terms, it's now 1 plus x. And that's obviously a linear function. It would have a slope of 1 and an intercept of 1. And so looking at that, that's exactly what this is, right? It's 1 plus x, just a graph of a straight line. If we go on to the 3rd term, so if we go now to here, we'd have 1 plus x squared. That should look like a parabola, right? Because it would be degree 2, it would have it would have roots and whatever. But basically, notice, again, what this is graphing now is 1 plus x squared. As I move the slider, more and more terms of the power series are being graphed. And currently, what you'll notice is really blue and green don't really look anything alike. But starting from the beginning, right, it started with 1. And, as I'm adding more terms, it's actually starting to look a little bit more like the graph of green. And if I keep going, notice if I go to 3 terms, 1 plus x squared plus x cubed, now, again, it looks like a degree 3 polynomial. But if I keep, the problem with polynomials is they always go to infinity. Polynomials can never look exactly like these weird functions. But if I keep going, it's sort of like building a polynomial to represent another function. So notice if I keep going 7, 8, 9, 10 terms and go all the way up to 20 terms in the polynomial, notice that blue and green are virtually indistinguishable. They look exactly the same. And that's exactly the point, that an infinite polynomial, if we could go to infinity with that polynomial, the infinity will, the polynomial will converge to the function. That's exactly what this formula says, right? Is that 1 over 1 minus x is equal to this. Now, remember, the interval of convergence was -1 to 1. It only converged for those specific values. And actually, if you look at the graph, notice that where it connects together, it only works from -1 to 1. That's the whole point of why the interval of convergence, right? If we plug in 3, that formula is not going to make any sense, but it will converge on the particular interval. And if you just click the little play button, it will actually continue with the view. And why I think this is kind of interesting to view, it sort of looks like wrapping a string around something. If you're taking a string and wrapping it, it kind of looks like you're spinning it around it. And, it's a very interesting visualization idea. And basically, as I'm adding terms, the series will converge to the function. But obviously, we technically need to go to an infinite number of terms to actually make it exactly right. But as we get to say 5 or 7 or 10 terms of that expansion, it gets closer and closer and closer. And sometimes another idea is that sometimes you can use like 3 or 4 terms in expansion to do approximations. And that's how a lot of calculators work. Another thing we're going to talk more about later. Anyways, that with that, we're going to do visualizations now. So let's actually talk about, let's get back into what is Maclaurin series. Sorry, I know it's been a very long setup for this, but so how do we solve Maclaurin series? That's the next thing. And basically, so this idea was first discovered, as far as we know, by a man named James Gregory in the, I think it was the early 1600s. Now, he didn't actually publish his findings because he thought he was just rediscovering Sir Isaac Newton's. Newton did a lot of math regarded to planetary motion, and he thought he just rediscovered Newton's method of doing things. And actually, Newton knew about power series to some degree, but basically, they never really formalized it. They never published math. They never published these ideas. So the first person to actually publish these ideas was named Brooke Taylor in the early 1700s, and that's why we call them Taylor series. But he was the first person to publish these things and really prove. He actually did a lot of hardcore math regarded with infinite series, as we've been studying, kind of to the next level, in order to really prove the convergence that these functions work, even though people had known about them for a little while. And then a little later, another mathematician named Colin Maclaurin did a ton of math specifically with Taylor series centered at 0. A lot of what we're going to do in our class is figuring out using Maclaurin series, and you'll see why Maclaurin series are more useful than Taylor series as we do it. But essentially, the only difference is Taylor series are centered at anything. And so just to do a quick recap, remember a power series is centered at 0 if it's just x to the n, if there is no minus a. But if it's centered at another value, say x is centered at 5, it's just basically the only difference between them. They're basically the same thing. So Matt, what I'll do in class sometimes I'll call them Taylor series, or I might call them Maclaurin series. In my brain, they're the same thing. Maclaurin series is just a specific case to a Taylor series. And yeah, so if they're centered at 0, they're actually a lot more useful. And all of my visualizations are for Maclaurin series. And again, we'll talk about why that is. But the question is, so how did Taylor do this? How did Taylor figure out a formula? And basically, if you look up these things on the internet, you'll find these formulas: Taylor series formula, Maclaurin series formula. What I wanted to show you guys is why. How did they figure these things out? So basically, he started with a very simple assumption. He said, well, let's assume that the Taylor series exists for a function. And so what that means is, if we have a mathematical function, it means it can be represented using an infinite series. Like, for example, e to the x is 1